Hello, it's Richard Hammack's Calculus 1. We are in part 5 of the course on integration. We've arrived at lecture 42, the Fundamental Theorem of Calculus. This is a big idea that ties together a lot of different things we've talked about in the course. To motivate it and to put it into context, let me say a few words about where we've been and where we're going with it. We've spent some time talking about the problem of finding the area A under the graph of a function f. And we got a formula for it. The area equals the limit as n goes to infinity of this Riemann sum of the areas of n rectangles. That led to a major definition. The definite integral from a to b of f of x dx, by definition, equals the number, which is the limit from our area formula. Let me point out here and emphasize that the definite integral from a to b of f of x dx is a number. It's got a variable in it, x, but it works out to be a number. So it really doesn't matter what variable we use there. We could use different variables like y or t. So for instance, the definite integral from a to b f of x dx, that's a number that's also equal to the definite integral from a to b of f of t dt. The actual variable you use is immaterial. I say this because there's going to be a point in today's lecture where we've already used x in one context, and then we're going to want to set up this integral, and we'll have to use it this way with a different variable. We say variables x and t that you see here and here are so-called dummy variables because it really doesn't matter what variable you use. They're just kind of going along for the ride, and the integral works out to be a number, has nothing to do with the variable. Having said that, let me talk about today's goal. We're going to establish what's called the Fundamental Theorem of Calculus. And it comes in two parts, part 1 and part 2. And it's really going to be part 2 that we're most interested in, that's most useful for us. What part 2 is going to say is the following, that this definite integral from a to b f of x dx, this expression that equaled this limit that we never wanted to work out, it's actually equal to a really simple expression involving antiderivatives of f. And that's going to be incredibly useful because it's going to allow us to compute definite integrals very easily without working out a limit. Now, part 2 is going to come out of part 1. So we're going to talk about part 1 of the Fundamental Theorem of Calculus first. I'm going to start with a motivational example for the Fundamental Theorem of Calculus, part 1. We'll look at a certain phenomenon involving a function f, and that phenomenon is going to be an instance of the Fundamental Theorem of Calculus, part 1, and at the end of the slide, I'm going to write it down at the bottom. The function I have in mind is f of x equals x plus 2. It's a straight line with y-intercept 2 and slope 1 as graphed here. In this problem, we're going to consider the area under f of x between 0 and x. And here x just represents some number, some positive number. So here's the picture. Here's 0, and here's x, whatever it happens to be. And there's this shaded region under the curve between 0 and x. And that's some number of square units of area. Now notice that that area depends on what x is. If you make x bigger, like this, that area is getting bigger too. It's really a function of x. The area under the curve depends on x. So it's a function, let's call it a of x. So whatever x is, a of x stands for the number of square units of area in the shaded region. And again, as x gets bigger, a of x gets bigger. If you then made x smaller, a of x is getting smaller. It's a function of x. It depends on x. And let's think about making a formula for this function a of x. The shaded region consists of two shapes, a rectangle of height 2 on the bottom and a triangle on the top. So as x gets bigger, the base of that rectangle gets bigger, and the base of the triangle gets bigger, and the height of the triangle gets bigger. The rectangle always has height 2. And let's think about finding the areas of these things. The base of the rectangle is x units. The height of the rectangle is 2 units. So the area of the rectangle is 2 times x. What about the triangle? Its base is x, and this line has slope 1, so the height of that triangle has to be x as well. So the area of that triangle is 1/2 base times height, so it's 1/2 x times x. Let's write that down. This function a of x equals the area of the triangle plus the area of the rectangle. The area of the triangle is 1/2 base times height, that's 1/2 x times x, and the area of the rectangle is height times base, that's 2 times x. So our a of x function is really simple. It's 1/2 x squared plus 2 times x. So whatever x is, 1/2 x squared plus 2x, that equals the number of square units of area in this region. I want to point out a connection between a of x and our original function f. The function we started with was f of x equals x plus 2. The area under that function, a of x, was 1/2 x squared plus 2x. And there's a striking connection between these two functions a and f, and you probably see it. If you take the derivative of a of x, you get x plus 2, you get f. The derivative of 1/2 x squared plus 2x equals x plus 2. The derivative of a of x equals f of x. What this means is this a of x, the area under the function, is an antiderivative of the function. And that is the Fundamental Theorem of Calculus, Part 1, and its basic idea. The Fundamental Theorem of Calculus, Part 1, can be thought of as stating that the area a of x under the graph of a function f of x is an antiderivative of f of x. Now the actual statement, we'll do that on the next page. It's a little more precise, but this is the basic idea of Fundamental Theorem of Calculus, Part 1. The area under a function f is an antiderivative of that function. Let's take that basic idea and make it precise. Here's a summary of the example from the previous slide. We've got our function f and a shaded region under f between 0 and x. And that shaded region has a of x square units of area. A of x is a function of x. If you change x, the shaded region changes, so its area changes, so a of x changes. A of x is a function of this x. In this picture, x is the right-hand edge of our area. The only difference between this picture and the one on the previous slide is that previously this was an x-axis, but since x already stands for the number that's the end of this area, let's call this a t-axis so we avoid any possible confusion. So our function, whereas previously it was y equals f of x, now it's y equals f of t. And the area under the graph of f of t between 0 and x, whatever x is a of x. On the previous slide, we saw that the derivative of a of x equals f of x. Let me fine-tune that a little bit. This area a of x, we know that's equal to the integral from 0 to x, f of t dt. That integral gives the area under the graph of f of t between 0 and x. So in this equation, let's just replace the a of x with what it's equal to. It's equal to this integral. And we get the derivative of the integral from 0 to x, f of t dt, equals f of x, just by making this replacement. Let me pause and point out that this integral from 0 to x, f of t dt, it's a number that depends on x, so it's a function of x. And the equation over here is saying that the derivative of this function of x equals f of x. This statement, in essence, is the Fundamental Theorem of Calculus, Part 1. The only difference really is that you may not have 0 as the left-hand edge of your area. It could be some other number a. The Fundamental Theorem of Calculus is going to say that the derivative of the integral from a to x, f of t dt, equals f of x. Let me write that down carefully. Here it is, the Fundamental Theorem of Calculus, Part 1. If f is continuous on the closed interval from a to b, as it is in this picture, here's a and here's b, then the function a of x, which equals the integral from a to x, f of t dt, is differentiable on the open interval from a to b, and its derivative is dx of the integral from a to x, f of t dt, which equals f of x. Compare that with this picture. You've got this closed interval from a to b, and you pick an x, could be anywhere between a and b, and you get this shaded region, and the function a of x equals the integral from a to x, f of t dt. That's going to change depending on what x is, so that's a function of x. The Fundamental Theorem of Calculus says the derivative of that function equals f of x. I've drawn this picture as if a of x actually equals area, and that's the case when this function is positive on the interval from a to b, as you know. But it may not be positive, in which case the integral from a to x, f of t dt isn't necessarily area, but it still has a value that depends on x. The Fundamental Theorem of Calculus says that the derivative of that integral from a to x, f of t dt, equals f of x. There's a lot going on here, and it takes a little while for this to sink in. Let's look at an example. So first, up at the top of the slide here, let me remind you of the Fundamental Theorem of Calculus, Part 1. If f is continuous on a closed interval from a to b, then the function a of x, which equals the integral from a to x, f of t dt, is differentiable on the open interval from a to b, meaning it has a derivative, and its derivative is dx of the integral from a to x, f of t dt, which equals f of x. Let's take an example. In this example, our function f of t is sine of t plus 2. So it's the graph of sine of t moved up 2 units. And let's make a equal to pi. So we have a shaded region under the graph of this curve between a, which is pi, and x. And that shaded region has an area that depends on what x is. You increase x, you get more shaded region, so the area of that shaded region increases. The area of this shaded region under the curve between pi and x is the integral from pi to x sine of t plus 2 dt. And again, that's a function of x. The value of this integral is a number that depends on x, so it's a function of x. And what the Fundamental Theorem of Calculus, Part 1, says is that the derivative of the integral from pi to x sine of t plus 2 dt equals the function f of x, which in this case is sine of x plus 2. Now, it's sine of x plus 2, not sine of t plus 2, because remember, this is a function of x here. The t was just a dummy variable. The value of this function depends on x, so its derivative needs to be a function of x. And the Fundamental Theorem of Calculus says it's sine of x plus 2. That's the fundamental theorem of calculus, part 1, in this example. This may look a little bit cryptic, and perhaps it is, but we are shortly going to move on to the fundamental theorem of calculus, part 2, that falls out of the fundamental theorem of calculus, part 1, and it's very useful. But before moving on to part 2, I'd like to give you a quick sketch of a proof of the fundamental theorem of calculus, part 1, why this derivative equals f of x. If you'd like to just accept this equation on faith, or maybe save the proof for later and come back to it, that's fine. Just fast forward through this slide and pick it up from there. You'll be fine. But on this slide, we're going to show why this derivative equals f of x. And for our sketch of a proof, it's probably best to think about this f of t as being positive on the interval from a to b. So this a of x, which equals this integral, is area. What we need to do is show that the derivative of the integral from a to x f of t dt equals f of x. And in this setup, that integral is the function a of x. So we need to show that a prime of x equals f of x, that this derivative equals f of x. We're going to use one of our definitions of a derivative. By definition, a prime of x, this thing we want to show is equal to f of x, equals the limit as h goes to 0, a of x plus h minus a of x over h. Remember, that's one of our definitions of the derivative, a prime of x. And we want to show that this limit actually equals f of x. I'll begin by drawing a picture of the situation here. Here's our function f of t, and a of x is the shaded area between a and x. So the a of x that occurs right here in this limit, that's that area of the shaded region. There's also in this limit an a of x plus h, and x plus h is just a little bit past x. Think about h as being positive. So x plus h is right there. And the a of x plus h, that would be the total shaded region area between a and x plus h. This light gray area together with this dark gray area. That's the a of x plus h. In this denominator, or this numerator, we have a difference, a of x plus h minus a of x. And what would that be? This entire shaded region is a of x plus h, and the light shaded region is a of x. So the dark shaded region all by itself is a of x plus h, the entire shaded region, minus a of x, the light shaded region. So this difference on the numerator is equal to this dark shaded region right here. Now on this picture, let's let little m be equal to the smallest value that f of t takes on between x and x plus h. So it'd be right here. That's our smallest f of t value on this little interval here. Also, let's let big M be the largest value that f of t takes on, where t is between x and x plus h. So in this picture, big M is right here. Now, I want to point out that there's a little rectangle right here of height little m and base, the distance from x to x plus h, which is h. That little rectangle right there is totally contained in the dark shaded area. So the area of this little rectangle here is less than or equal to the area of the dark shaded region, which is a of x plus h minus a of x. So this little rectangle right here, whose area is base h times height little m, h times m, is less than or equal to the area of the dark shaded region, which is a of x plus h minus a of x. Likewise, look at this tall rectangle of height big M and base h. That tall rectangle completely contains the dark shaded region. So its area, which is h times big M, is greater than or equal to the dark shaded area, a of x plus h minus a of x. So we get this chain of inequalities here. And the next thing we're going to do is divide every part of that by h. And in so doing, the h's here and here cancel out, and we get an h on the denominator. So we have this expression, a of x plus h minus a of x over h, greater than or equal to little m, but less than or equal to big M. Now, this little m that's right here, if you think about h getting smaller and smaller and smaller, x plus h is getting closer and closer to x, that value of little m, it gets closer and closer to f of x as x plus h squeezes into x. And likewise, big M in general is getting closer and closer to f of x also as h gets closer and closer to 0, as x plus h gets closer and closer to h. So what we're going to do next is take the limit as h goes to 0 of each part of this inequality. We get the limit as h goes to 0 of m, and remember that limit is getting, that m is getting closer and closer to f of x, so the limit as h goes to 0 of m is equal to f of x. And over here, the big M, as h goes to 0, it's getting closer and closer to f of x. So the limit on the left and the right, they're equal to f of x. And what about the limit in the middle? Well, by definition, that's just a prime of x. So we get f of x less than or equal to a prime of x, less than or equal to f of x. So a prime of x is caught between f of x and f of x. And there's only one way that can happen, and that's if a prime of x equals f of x. So there you have it. We've just shown that a prime of x equals f of x, that this derivative equals f of x. That's a quick sketch of the proof of the Fundamental Theorem of Calculus, Part 1. You can think about this as our last derivative formula. You'll remember at the first part of this course, or actually more accurately in the part 3 of the course, we derived a lot of rules for derivatives. There were like 25 different rules. And now we have another derivative rule. The derivative of a function looks like this, that has this form, equals f of x. It's our last derivative formula. With that, let's move on to the Fundamental Theorem of Calculus Part 2, which is the most useful formulation of the Fundamental Theorem of Calculus. As I mentioned before, the Fundamental Theorem of Calculus Part 2 gives a simple definite integral formula. We're going to work out a simple expression for the value of the integral from a to b f of x dx. We'll work it out on this page. We'll get an answer. We'll put it right there. And then what's in this blue box will be the Fundamental Theorem of Calculus Part 2. To get it, we're going to start with the Fundamental Theorem of Calculus Part 1, which states that the derivative of the integral from a to x f of t dt equals f of x. In particular, that means that this integral is an antiderivative of f of x because its derivative equals f of x. And let's write that down. The integral from a to x f of t dt is an antiderivative of f of x. What we're going to do now is let big f of x be any antiderivative of little f of x, any antiderivative that you could find. So we now have two antiderivatives of little f of x. We've got this integral, and we've got this big f of x. And we know that any time that we have two antiderivatives of a function, one will be the other plus a constant c. So that means this antiderivative of little f of x equals the big f of x plus c. In our next step, we're going to plug in the value x equals a into this expression. So everywhere we see an x here and also here, we plug in an a. We get the integral from a to a f of t dt equals big F of a plus c. Now the integral from a to a f of t dt, we have an integral property that says that's equal to 0. Look at this equation we get. 0 equals f of a plus c. You could solve for c. You get c equals minus f of a. Now that we have c equals minus f of a, let's go back up to our expression here and replace c with what it's equal to, minus f of a. We'll put a minus f of a right there, and we get the integral from a to x, f of t dt, equals big F of x minus f of a. Now, at this point, what we're going to do is, for this x, we're going to plug in the value x equals b. So here and here, we just plug in b, and we get the integral from a to b, f of t dt, equals big F of b minus big F of a. We've got a really simple expression for this definite integral now. And if you look at it, we've got a variable of t, but there aren't any x's anywhere in this expression now that we've plugged in x equals b. So we can just change that t back to an x. And what we get is the integral from a to b of f of x dx equals big F of b minus big F of a. So we've concluded here on this page that if big F is any antiderivative of little f, then the integral from a to b of little f of x dx equals big F of b minus big F of a. That's the fundamental theorem of calculus, part 2. Let's write it down very carefully. Part 2 of the fundamental theorem of calculus comes from part 1, so there's a little bit of language we need to insert to assure that part 1 applies. Here's a careful statement. Fundamental theorem of calculus, part 2. If little f is continuous on the closed interval from a to b, and big F of x is any antiderivative of little f of x, then, as we worked out on the previous slide, the integral from a to b, f of x dx, equals big F of b minus big F of a. That's a pretty remarkable statement. You'll remember that by definition, the value of this definite integral was a limit of Riemann sums that was really hard to work out. Now we have a simple expression for it, big F of b minus big F of a. So finding this definite integral is as easy as finding an antiderivative of little f, plugging in b and plugging in a and doing the subtraction. Let's work out an example. Let's find the integral from 0 to 2 of x squared dx. Here's the graph of x squared, and you can see that this definite integral is going to equal that shaded area right there. It may look familiar because back when we were talking about area, we actually worked out this exact area by taking a limit of Riemann sums. And if you remember, we got a value of 8/3. So actually, we already know what this integral equals. It's 8/3. But let's work it out using the fundamental theorem of calculus, part 2. Part 2 says that finding this integral involves finding an antiderivative of x squared, a big F. So let's start there. We're looking for an antiderivative of the function little f of x equals x squared. Well, that's easy. It's big F of x, which is the indefinite integral of x squared dx, or 1/3 x cubed plus c. So good. But notice that the statement of the theorem up here says we can use any antiderivative. Doesn't matter what c is. So let's make life simple and take c equals 0. So our antiderivative of x squared is big F of x equals 1/3 x cubed. So now we apply the fundamental theorem of calculus, part 2. The integral from 0 to 2 of x squared dx equals big F of 2 minus big F of 0. The 2 is the b, the 0 is the a. So then we just have to plug these two numbers, 2 and 0, into our big F and do the subtraction. Well, big F of 2 is 1/3 2 cubed, And big F of 0 is 1/3 0 cubed. So we just do that math and we get an answer of 8/3. Just as we did before when we were talking about area, but it's so much simpler with the Fundamental Theorem of Calculus, Part 2. Before we move on to another example, I want to point out this C. The statement says we can use any antiderivative of f of x, so we just took c equals 0 and used this antiderivative. But what if you used a different value of c other than 0? That's okay too. Notice what you'd be doing is you'd be adding a c here and subtracting it right there. So no matter what c is, they're going to cancel out. So when applying the Fundamental Theorem of Calculus Part 2, make life simple for yourself and just take c equals 0. Let's look at another example. Let's find the area of this shaded region. It's below the graph of cosine of x and between x equals negative pi over 2 and pi over 2. Well, we know from the area interpretation of the definite integral that this shaded area is the integral from negative pi over 2 to pi over 2 cosine x dx. So we just need to work out the value of this definite integral. And we can use the Fundamental Theorem of Calculus Part 2. It involves finding an antiderivative of cosine of x, a big F of x. So let's think about that. An antiderivative of cosine x would be the function big F of x equals the indefinite integral of cosine x dx, which is just sine of x plus c, but we're going to make that c 0. So big F of x is just equal to sine of x. Now applying the Fundamental Theorem of Calculus Part 2, we get the integral from negative pi over 2 to pi over 2 cosine x dx equals big F of pi over 2, or sine of pi over 2, minus big F of negative pi over 2, or minus sine of negative pi over 2. Sine of pi over 2 is 1. Sine of negative pi over 2 is minus 1. And you do the subtraction, and you get an answer of 2. So this shaded area here, remarkably, is 2 square units of area exactly. It's kind of surprising because you'd think that area would involve pi or something like that, but it's exactly 2 square units of area. And it was so simple with the Fundamental Theorem of Calculus, Part 2. Before doing more examples, let me talk about some notation. The Fundamental Theorem of Calculus Part 2 involves the expression big F of b minus big F of a. And sometimes, especially when big F is a complicated function, that may be a lot of writing, and you want to abbreviate it. And here's a standard abbreviation. We denote this difference by this symbolism. We have a big F of x enclosed in square brackets, and on the right use subscript with a and superscript with b. We read this as big F of x from a to b, and by definition, it just stands for the difference big F of b minus big F of a. What you get when you plug in the b to x and subtract off what you get when you plug in the a. And we'll use this shortly. I should point out that in some textbooks, this left-hand bracket is not there, and big F of b minus big F of a will be denoted this way, which again you read as big F of x from a to b, and it stands for this difference. And in other texts, just a vertical bar rather than a bracket is used. You'd read that as big F of x from a to b, and it stands for this difference. But in my lectures, I'm going to use this notation exclusively, where the big F is enclosed completely in square brackets. So with this, we can rephrase the Fundamental Theorem of Calculus Part 2 slightly. It states that the integral from a to b, f of x dx, equals big F of x from a to b. And again, that notation just stands for big F of b minus big F of a. Let's do another example. The integral from 2 to 4 of x cubed dx. According to the Fundamental Theorem of Calculus Part 2, what we need to do to get an answer is find a big F of x, an antiderivative of x cubed, and go from a to b. So We're looking for an antiderivative of x cubed to put right here, and then go from 2 to 4 there. Now, what's the antiderivative? Well, that's the integral of x cubed dx. That'd be x to the 4th over 4 plus c. And just make that c equal to 0. So our big F of x here is x to the 4th over 4. So our answer is going to be x to the 4th over 4 from 2 to 4. So you plug in the 4 into x to the 4th over 4, minus what you get when you plug in the 2. So you get this difference. 4 to the 4th over 4 is 64, 2 to the 4th over 4 is 4, and the difference is 60. So the definite integral from 2 to 4, x cubed dx equals 60. Here's another example. The integral from 0 to 1 of 1 over 1 plus x squared dx. So according to the Fundamental Theorem of Calculus Part 2, we're looking for an antiderivative of 1 over 1 plus x squared to put here, and then we'll evaluate from 0 to 1. So what's an antiderivative of 1 over 1 plus x squared? If you think about it for a moment, you have an integral formula for that. An antiderivative of this function would be tangent inverse of x plus c, but again, the c is 0. So we just get tangent inverse of x from 0 to 1. Plugging in the 1 and subtracting off what you get when you plug in the 0, we get tangent inverse of 1 minus tangent inverse of 0. Tangent inverse of 1 is pi over 4. Tangent inverse of 0 is 0. So our answer is pi over 4. Another example, integral from 1 to 4, square root of x plus x dx. Now looking ahead a step, we want to find an antiderivative of square root of x plus x. So you probably want to write that square root of x as a power so you can use the power rule. So let's do that conversion. We get this integral. And the Fundamental Theorem of Calculus Part 2 says we need to find an antiderivative x to the 1/2 plus x, put it here between the brackets, and then go from 1 to 4. So let's work out that antiderivative. We can use the power rule for the antiderivative of x to the 1/2. You get 1 over 1/2 plus 1, x to the power of 1/2 plus 1, plus, then an antiderivative of x would be 1/2 x squared. Put that between the brackets and go from 1 to 4. Now I'll quickly simplify this. The reciprocal of 3/2 is 2/3. Convert this power of x to a radical. And now let's plug in the 4. So you get 2/3 square root of 4 cubed plus 1/2 4 squared, minus what you get when you plug in the 1 to this antiderivative. Working this out, I get 16 over 3 plus 8 minus 2/3 plus 1/2, and that works out to 73 over 6. So it's simple to find antiderivatives with the Fundamental Theorem of Calculus, Part 2. That's it for today, and we've covered a lot of ground. We talked about the Fundamental Theorem of Calculus, Part 1, which says the derivative of this integral equals f of x. And from it, we got the very useful Fundamental Theorem of Calculus, Part 2, that says that the integral from a to b of little f of x dx equals big F of b minus big F of a, where big F is any antiderivative of little f. And we can abbreviate that as big F of x from a to b. At this point, it's vital to get lots of practice. So work some of these problems, especially ones involving finding definite integrals with the Fundamental Theorem of Calculus. There's still more to say about this topic. Up next, in Lecture 43, we'll continue talking about the fundamental theorem. But for now, practice. I'll see you next time, and goodbye.